All right, so the last section of 15, or the last part of 15.2. Did I write 10? I'm confused. I get confused because two of my classes are in chapter 9 and 10, and I switch those around, and then yeah.
Oh, that got me really confused.
That would go. We go back to doing what was chapter 10, polar coordinates.
Let's go back to 10 folks.
All right. So just a quick summary of what we talked about with line integrals. So for a scalar field, we have z equals f of xy, and we have a smooth curve c. The line integral of c along c of our function f of xy ds, we said was the integral from a to b. We're moving along the curve of f of r of t. We're parameterizing our curve. We express our function in terms of the parameters, and then we multiply by r prime of magnitude of r prime dt, t dt. So that was how we evaluated line integral when we had a scalar field. And if we had a vector field, and we still have our smooth curve C, our line integral of our vector field, C of, we wrote f dot dr, was the integral from, we said was also the integral of f dot the unit tangent vector ds, and we evaluated that by integrating from a to b of f. We expressed our vector field in terms of our parameterized curve, f of r of t dot r prime of t dt. So that's what we've spent the last couple of times talking about. What we want to do today is find a relationship, find a connection between these two forms of line integrals. Because when we do this vector line integral, we end up taking the dot product. So we're integrating a scalar, and here we're integrating a scalar. So our vector becomes a scalar. So that's one connection. But we want to make that connection a little more explicit. What's actually happening here? How can we make a connection between this vector line integral and this scalar line integral? So that's what we're going to do. So I'm just going to say our connection. It's always nice when we can think of two different things as just different aspects of one single thing. So what we're going to do is we're going to let f, and we're going to do this just for two variables. We can extend to three variables just by adding another component. So we're going to use our notation m I hat plus n j hat. And we're going to say our curve is this vector valued function, r of t, and we're going to say that's x of t I hat plus y of t j hat. And we're going to form, when we do our line integral, we take f dot r prime. So we're going to form that dot product. F dot r prime is m dx dt plus n dy dt. So that's our dot product when we form that dot product. So our integral, our line integral of this vector field over this curve f dot dr ends up being the line integral over our curve of m dx dt plus n dy dt dt. And we can rewrite that as the line integral over our curve of m dx plus n dy. The dt's away. And we end up with the line integral of this vector field is the sum of these two scalar line integrals, m dx plus n dy. And if we extended this to 3 dimensions, we just have a k component. We just have a p dz in our integral. So our line integral of f over this curve turns out to be the sum of these two scalar line integrals. So that's our connection between the vector line integral and the scalar line integral. This is how we make that connection explicit. We call this form, we call this the differential form of a line integral. And it's going to be useful to express our vector line integrals in differential form as we move forward. There'll be times when it's beneficial to express our line integral in this form. It'll allow us to do some nice things when we have certain conditions that are met with our field. Our differential form of our line integral is going to be able to do nice things with it. So this is our differential form of our line integral. So I just want to do a couple of examples of using this differential form rather than going through this process of parameterizing our curve and expressing the f in terms of the parameter, et cetera, et cetera. We're going to use this form. So questions on how we came up with this differential form. Okay. A couple of important notes, and we've talked about this as we went on. So I just want to re-emphasize these before we do these examples. The magnitude of our line integral is independent of the parameterization of the curve. So we can parameterize our curve however we want. When we find our line integral, the magnitude is not going to change. For a scalar line integral, nothing will change. We said we could interpret the scalar line integral as the area, an area of a fence, that lateral surface area, or as a mass of a wire. That mass isn't going to change if we integrate in one direction versus the other direction. For a vector line integral, the orientation of the curve can affect the sign of the line integral, either positive or negative. So it's going to affect the sign of the line integral of f dot dr and our differential form, because our differential form is a way of expressing this in the scalar form. And I'm going to write the full p dz, so if we're talking about three dimensions. So the opposite orientation changes the sign of the line integral. because if we're going in the opposite direction, our unit tangent vector points in the opposite direction, and f dot, the dot product of our field with the unit tangent vector has an opposite sign. But the orientation does not affect a scalar line integral. So the integral c of f of xy ds is not affected. That area doesn't change, that mass doesn't change if we go two different directions. So the different orientation changes the sign of our vector line integral. So that will be something to remember as we move forward to thinking about the parameterization and how we move along the curve, and whether we're talking about a vector field or a scalar field. All right. Are we good there? All right, let's look at a couple of examples. So this first example, we're just going to evaluate a line integral in differential form. We want to evaluate this line integral to xy dx plus x plus 3y dy. And along our curve, C is an arc on y equals x to the 3/2 from 0, 0 to the point 4, 8. So this is a line integral in differential form. So from the way it's set up, we can say that m is 2x minus y, and n, in the notation we used, was x plus 3y. And we need to find dx dt and dy dt, so for our parameterized curve. Well, since we have y equals f of x, what makes sense? What makes the most sense for our parameter on this curve? Do we need to change anything about this? We already have the relationship between x and y, right? So let's let x be the parameter. So our parametric equations are x equals x and y equals x to the 3/2. So what we need to do when we evaluate these line integrals in differential form, if x is our parameter, we're going to express everything here in terms of x. We could let t be our parameter, and then y would be t to the 3/2 and express all of this in terms of t. Same thing. But since we already have this relationship, we'll just express everything in terms of x. So dy, we need to express dy in terms of dx, in terms of x. So take the derivative here. dy is 3/2 x to the 1/2 dx. And x is varying from 0 to 4. So now I'm just going to plug all of that stuff into these expressions, and I'll have just an integral in terms of x. So we end up with the integral from 0 to 4 of 2x minus x to the 3/2 dx plus x plus 3x to the 3/2, and then here's my dy, times 3/2 x to the 1/2 dx. So there's my entire integral. So I just end up with this nice integral in terms of x. If I collect like terms, multiply, distribute here, and write this a little more nicely, I end up with the integral from 0 to 4 of 9/2 x squared plus 1/2 x to the 3/2 plus 2x, and then we all have a dx, and if I evaluate that I end up with 592 bits. So this lets me avoid finding r of t. We don't have to find r prime. We don't have to do the dot product. When we have our line integral in differential form, we just need to express everything in terms of one variable. All right, we good there? So just a little different way of looking at line integrals. Again, we'll talk about conservative fields next time, and we'll use this differential form. And then after we talk about conservative fields, we'll talk about our first big theorem. Well, I guess next time we'll talk about a big theorem. We get to talk about the fundamental theorem of line integrals, which is a nice thing. So we know the fundamental theorem of calculus. We'll talk about the fundamental theorem of line integrals. And that will lead us into Green's theorem, which is really our first big theorem of the chapter. And Green's theorem is a really nice thing that has to do with line integrals on closed curves. All right, let's look at one more example. So we want to, in this example, we want to find the line integral of f dot dr on two curves. And we want to explain the results. And we're going to do our line integrals. We're going to do these in differential form. So our field f for this example is x squared y I hat plus x y to the 3/2 j hat. And R1, our first curve, is t plus 1 I hat plus t squared j hat from 0 less than or equal to t less than or equal to 2. So let's practice using our differential form. So for our field, m is x squared y, and n is x y to the 3/2. And x from our curve, x equals t plus 1. So dx equals dt. And y equals t squared. So dy equals 2t dt. And the reason we're doing all this is we want to say that our line integral is m dx plus n dy. So we want to evaluate our line integral in this differential. So we're going to express everything in terms of t. Dx is dt, dy is 2t dt. So our line integral becomes the integral t equals 0 to 2 m is x squared y times dt plus, oops, and I forgot, I need to express this in terms of, I wrote x and y, and I want to write it in terms of t. So x squared is going to be t plus 1 squared times y times t squared dt plus xy to the 3 halves, so plus t plus 1, and then I get t squared to the 3 halves dt. So that was my line integral. To evaluate this, distribute, square this, distribute, we just end up with line integrals of polynomials. Yes? dy dt, yes, this should be, I forgot my 2t. Thank you. dy is 2t dt. So we would square this, distribute, do this, distribute, evaluate this in terms of t. We just end up with a with an integral in term, just a polynomial integral, so power rule, and this evaluates to 256 fifths. All right, let's look at our other curve now. So we want the same field. So R2 equals 1 plus 2 cosine t I hat plus 4 cosine squared t j hat from 0 less than or equal to t less than or equal to pi over 2. So that's our second curve. So we still have m and n, same m and n that we had before. Here, x equals 1 plus 2 cosine t. So I'm trying to find my dx so I can express everything in terms of t. Dx is minus 2 sine t dt. Y equals 4 cosine squared t. So dy equals minus 8 cosine t sine t. And then I'm going to substitute these in for x and for y for my m and n in my line integral for this second curve. So we have the integral from 0 to pi over 2. 1 plus 2 cosine t squared times 4 cosine squared t times minus 2 sine t dt. So I'm just substituting for x and for y and for dx. And then I'm going to say plus, and I'm going to go down to another line here, plus. So I'm going to put a bracket around there. Plus, for my y component here, I end up with 1 plus 2 cosine t times 8 cosine cubed t times minus 8 cosine t sine t dt. And we could go through a lot of work to evaluate this, or we could put it in our calculator and evaluate this. This would take a lot of work to simplify, and with all these trig things to powers. So one way or the other we're going to evaluate this. I would probably do this in my calculator, and it turns out that this comes out to negative 256 fifths. Yes. Y is so y is to the x, y to the 3/2. So we're doing 8, or we're doing 4 cosine squared t to the 3/2 power. So we take the square root, we get 2 cosine t to the 3rd. So 2 to the 3rd is 8, and then we get the cosine. So this comes out to negative 256/5. We want to explain these results. What happened here? The sign change, that's a hint that it might have something to do with the orientation. So on R1, from 0 to 2, I'm going from the point 1, 0 to the point 3, 4. So on R1, so if I substitute my endpoints here, we're going from 1, 0 to 3, 4. And on R2, we go from three, 4. If I substitute t equals 0 into my parameters, I go from 3, 4 to 1, 0. So what happens here, what's going on, is these two parameterizations are, for R1 and for R2, are parameterizations of the same curve moving in the opposite direction. So we're going in opposite orientation. So this curve, this is a parameterization for what would this curve be? Some kind of parabola, some kind of parabola. Well, here we have a same kind of thing, but we're moving in the opposite direction. This is also a parabola because we have 1 plus 2 cosine t, and this is 4 cosine squared t. So it's a similar kind of relationship. We're just moving in opposite directions. So this was same curve, opposite orientation. So one parameterization takes us one direction, the other parameterization takes us the opposite direction. So the magnitude of our line integrals are the same, they just have different signs. And this one, I'm looking at this one, I'm thinking there's a better way. This one's, I think, ends up messy no matter what you do with all those trig functions. All right, questions there?
Or you can make it just basically one giant use of the first function.
So we have cosine, we have powers of cosine, and we have a sine t. So that's our du, yeah. And then for the second one, same thing. So yeah, maybe it wouldn't be that bad. It looks intimidating, but I think Max is right. Since we have this spare sine t out here, and the rest are just powers of cosine, we end up with u subs. And we end up with powers of cosine that we're evaluating from 0 to 2 pi. So it looks intimidating, and even just writing it out is not really that fun because you have to write all this stuff. But it's always nice when you simplify things, and this integral, it looks like it could be very ugly, turns into a nice u sub. All right, homework. There's not very much up there. Do you guys have, 4 days? Should I add some problems?
No.
Yeah, give us more. Give us like 10.
Give you 10?
You can do that.
Yeah, right? No, let's all do that.
10 more or 10 total?
Let's do 20. All we need more.
Let's just do the rest of the
All right, there we go.
That's right.